All right, let's get going. Um, Today is the last class where I will be streaming on Twitch, so Wednesday and Friday will be on Zoom. I'll send out an announcement for that as well, just as a reminder. And your final presentations list was published. I sent out an announcement about that as well. At least I'm pretty sure I did. I did not. Okay. Well, I mentioned it at least last time. But presentations are Wednesday and Friday. So Wednesday, we've got Team Retro, Halo Clone, BKB, and GUI Dancer going. Um, just again, 8 to 10 minutes presentation time. Just make sure everybody talks, describe what your project is, what you did, show what you have working, and if you are not done, that's fine. The deadline of the actual deliverable is not due until the 29th, so use that time to wrap up whatever you need to. There's also that extra credit test case, test specification if you want to work on that as well, if you feel you need it. But again, not intended to be a huge stressor for you. More of a let's talk with your classmates, show us what you're doing, make sure you hit all the key points, and it's not something terrible. At least you don't have to stand up in front of a classroom this time looking uncomfortable. You can be in your bedroom looking uncomfortable or wherever you're going to be speaking from. So I have that, and then Friday we'll do the rest of the teams. Also do a little bit of an exam review on Friday as well. I will post some like an exam review pretty shortly here as well, so that you can all have that ready to go. Questions at all? Everything look okay? Make sure that I don't forget this. If we are all good, then we can get on with our last chat. All right. Not sure if we'll do the slide-do or not yet today. Just kind of depends on how quickly and how slow I'm talking, or how slow I am talking. So we've got a lot to get through, and we have to get to your stuff. We have been speaking about lots of different topics in this class. Right? We've been going over all the different levels of design, project management, touch of implementation with our design patterns. And we recently started talking about testing, and I threw you into test-driven development. That is a new thing, new paradigm, I suppose. Newish. I'm getting older. Um, but testing has been around for a very long time. And basically ensuring that your software is doing what you say it should be doing and what your customer is expecting it to be doing are very important. And they're also kind of two different things. So we're going to basically be talking about verification and validation today. And there's a very fine difference between them. Basically, we're checking our projects to make sure they work. Now, with verification, we have dynamic and static verification. Basically, we're looking at things like return types, data structures, basic, that you're following some template of coding, basically. Dynamic, we're looking at behavioral properties, we're looking at algorithms, we're looking to make sure that decisions made at runtime make sense. And then testing, we have a whole bunch of stuff to talk about. So we'll sit on that and we'll get to it in a bit. But some lovely quotes for you all, first and foremost. So first of all, that's where I pulled these from. They're absolutely delightful. All code is guilty until proven innocent. Fast, good, cheap, pick any two. This is a good strategy for software design and software testing. This is a nice, clean one here. Quality is never an accident. It's always the result of intelligent effort, meaning you actually have to design quality software purposefully. And this is a good one here at the end. I like this one. It's more about good enough than it is about right or wrong. So this is something which is going to kind of become your mantra for software development. At some point, you have to cut ties and release it. Whether it is perfect or not will be a debate that you're going to have. There will never be enough testing. There will never be enough verification. You will never be guaranteed that it's going to be absolutely perfect. But at some point, it has to be good enough. And good enough means that it passes your test cases, it passes all of your code smell tests, it passes your internal barometer for ethical quality, and you're ready to give it to somebody else to use. So good enough is going to be, it sounds awful and it sounds kind of like one of those, half-arsed things about pushing out software quickly. But good enough means that you've passed your level of quality. Again, you're never going to get perfect software. It's a pipe dream. So V&V, verification and validation. This is a term that you will hear throughout your industrial or academic careers. Basically, it's going to come into this kind of interesting to say quote here. So verification, are we building the thing right? Validation, are we building the right thing? And these kind of sound like they're saying the exact same thing. And I know I've mentioned this, I think probably very early on in the class. But verification means that your software is doing what you say it is doing. So you have a requirement spec, you have a set of user stories, you have all of your design documents and all of your software artifacts. Verification means that you're taking all these artifacts and your software is doing what you said it's doing in all these Word documents and all these spreadsheets and all these figures. It may not be the right thing to build, but it's doing what you say it should be doing. So that's verification. Validation, on the other hand, means that you're taking this software package that you built and you're ensuring that it meets what your customer is expecting. And remember, customer requirements and your own internal requirements are usually different. Hopefully they're developed in parallel and together so that we know what everybody's doing. But hopefully you can kind of see the fine point here. Verification follows your specs, validation does what the customer is expecting. And these are kind of two different thought processes in software engineering. Usually there's verification people and validation people. The verification people tend to do things like formal proofing, for instance. So we're building models, we're using formal logic to actually discover if these programs are doing what their models are say that they're doing. The validation people tend to be running test cases in the wild. Like, let's go out with the customer, run test cases in their environment and make sure it's working correctly. To me, it's almost like we're using real world data in validation. Verification is more simulation in a way. And the definition will vary, honestly, person to person, because these, again, sound very, very similar. Now, we should be using these together, okay? You should do both, ideally. Make sure that it's following your specs correctly, make sure that it's following your customer specs correctly. And if you do both, and if you do a lot of them, your software will probably be good enough. It does not mean that it is free of defects. It does not mean that it is good enough for every single person on the planet, right? You're always going to find some edge case or some use case that you never anticipated maybe months after you release it. But that's the whole maintenance phase of software development, right? So V&V, we should be doing this. So let's talk verification first. I'm going to pop all these in. So I said we have dynamic, we have static verification, right? So dynamic means that we are checking behaviors. We are checking to make sure that we're making the correct decisions at runtime. Typically, dynamic verification, you can think of it like software testing. So I'm going to have a pre-built executable. I'm going to feed it test data, and I'm going to see what it does. Does it meet my test spec? Are we getting the expected outputs that we say we should be getting? Right? Think of your unit tests that we talked about. You give a function a particular input, you're expecting a particular output. But if that function returns something else, something's wrong. It's a behavioral issue, right? So we're basically seeing what's happening when the system's executing. You can extend this beyond testing, right? We can do model checking. we can generate a simulated model of our system, right? Think of like a flow chart where we're in state one, then state two, then state n, and these series of decisions that get us to state n is what we're expecting. But when we run, say, a model checking software and we see all these deviations from what we're expecting to happen, we may even have issues of logic in our diagrams and things of that nature. So dynamic, we're checking runtime behavior. Static analysis or static verification, this is where we're looking at the static, the stationary side of our software. So we're going to read through our code. We're going to read through the requirements, all of our artifacts, right? We can verify our requirement specs. We can verify our test specs. We can verify our class diagrams. But these are static things, right? They're not changing at runtime. And how do we do that? Static analysis for software is a completely, well, the next slide is going to be that. But we're basically going to be using software to check through it. If you're looking through requirements, you're probably having meetings where you walk through all the requirements, make sure they link to the correct test cases, that they're worded correctly. This whole procedure of you all revising your requirement specs for the final, you're basically doing a static verification test, making sure that your requirements are correct, right? So we could be walking through them. We could run correctness proofs, which would be a model checking type of thing as well. We can automate things on top of that. So here is an example of a static analysis tool behind the scenes. Question while I'm kind of going over this, any of you ever touch a static analysis tool before? If you've been in industry, there's a chance that you did. Not something many people seek out unless you want to learn about it. But these are pretty common when you're doing like a software build. You would run a static analysis tool of some kind. And I love that the last comment in chat is this weapon looks OP, and I've got static analysis up. Excuse me. Anybody ever use one of these? So I will say that when I was in industry, we had one added. It was part of our Visual Studio build chain. It's like we would have our code, we would run a build, it would run through, it would actually do the static analysis first, and then it would compile, and then it would build a binary file for the microcontroller we were using. But static analysis is a very powerful thing. We're going to look at our source code, say. We're going to generate a model from our source code. And this model could mean different things based on what you're looking for. So for instance, we might get a symbol table, or we might get an abstract syntax tree, or a call graph, which shows like how code flows from point to point. Abstract syntax tree, this would be like breaking down the various lines of code that you have. But what we basically get is a way for procedurally analyzing our source code. So how we used it at my company, it was a style checker. So I know all of you probably know and love that GVSU Java style guide. Basically, you can have tools like this enforce that guide. And we used it in industry where I worked for safety critical requirements. Like every if statement had to have an else case, regardless if you used it or not. That was just a safety thing to make sure that every branch was covered, right? We had particular styles for like naming variables and things of that nature. The static analysis checker would catch all those things, and it could be really annoying, but a lot of times it was there for a reason. Again, for us, it was a safety critical thing. It could just be for style, it could be for analyzing algorithms, just kind of depends on what you need it for. But this would be a step that basically goes over, your code and goes over your logic in your code. Maybe you're using a float instead of a double. It would catch that. Or a long instead of an int. Or a long instead of a float. Just kind of depends on what precision you need, right? So that is kind of the notion there. Now the question you may have is, can we use them together? Right? So can we use verification and validation kind of in sequence or in parallel? If we're doing verification, can we use the same thing for validation? And that's kind of an interesting question here. He said, subtly draining his coffee. Verification, again, is making sure our requirements do what they say they're doing. Validation means we're checking to make sure we're doing what the customer expects. And you could absolutely use them together, right? We could use verification tasks for validation, as long as we're ensuring we're checking customer requirements instead of our own internal ones. Or take it from the other side. We talked about traceability a while back, right? Let's link things together, link requirements to test cases, link test cases to code or something of that nature. We could link customer requirements to internal requirements, and then you have a direct linkage, one-to-one. This requirement implements this customer requirement. Sure, why not? All right, let's get into some of the heady stuff now. Software testing, probably one of the better quotes. So The Art of Software Testing is a great book if you're getting into the testing field. Testing is a process of executing a program with the intent of finding errors. But we only detect the presence of errors, not their absence. So this gets to the notion of what a successful test is, right? So when we did test-driven development, I warned you, don't write your code to pass tests, right? Even though that's the whole purpose of TDD. If you're doing testing, right, and I did not enforce it for you all this semester, but when you do testing, you want to see all those little green check marks pop up, right? You want all your test cases to pass because then you don't have to worry, right? Everything's good. But if all your test cases pass, that means you haven't caught the bug. And that can be a very troubling idea, right? Again, there's always going to be some bug. The more complicated your programs get, the easier it's going to be for them to pop up. I guarantee it. Now, a successful test is going to basically establish that you have an error, right? So we're going to find something and we're going to know how to fix that something, right? It might be an easy fix. It might take months of effort if it's a big problem, but at least you know what the issue is, right? But if everything passes on the first go, you know, I think it's the Eminem meme where something's wrong, I can feel it. If all of your test cases pass, what did you miss? Are you missing a test case? Does your software just kind of hang by a thread, right? Can be a troubling thing. So if we have test cases that fail, it means that we have errors, but if they're all passing, you have this uncertainty. Well, what are you missing? Um, so let's look at it a different way here. So we're going to have something called the test suite. So you've been developing test cases. Again, if you're going for that extra credit, that's a collection of tests. All right, so it's going to be a list of tests that you run through every time you build your software. The group of them is called a suite. So if your test suites pass, and you can have multiple test suites, depends on what you're kind of looking for. If they're all passing, doesn't mean that there's a problem that doesn't exist, right? It could be that your test suite, again, your list of test cases, if maybe it's not exercising your program correctly. And exercising a program is basically to take it through its paces. Check every single if statement, check every single possible condition, check everything. Again, realistically, they're never bug free. So let's see. There's a little bit of psychology that we can talk about here. And this is kind of an interesting thing that we don't really ever talk about in software development is your state of mind, right? We all assume you to be good little automatons that can write code day in and day out with some caffeine and maybe something chocolatey, assuming you're not dairy free, I guess. Then it's got to be vegan chocolate. But if you are going to go do testing, you have to be in the mindset to break something, right? You don't want it to pass. You want it to fail. Your goal as a tester is to pick this thing apart. And that's why we often don't want programmers to be testing their own code, because intuitively, whether you realize it or not, you do not want to break your creation, right? You don't want to see it fail. It's your little baby. So your goal as a tester, and I'm assuming you're taking the role of a full-on tester for this, set of slides, your goal is to break the program. Give it inputs that the programmer never expected. Use it in such a way that somebody might use it, but it completely breaks the flow of everything, right? We are trying to destroy this beautiful creation that somebody else made with the intent of making it better. Okay, so that's always the caveat. Make sure that what we're doing is useful, right? If you ever look at any video game tester out there, they probably hate video games after that point because their entire purpose is to play it in the most grinding, mind-numbing ways to find all the little edge cases, right? Let's back up into this mountain 300 million times, and maybe one time we leak through the edge of a mesh and we fall into negative space. Okay, how did we make that happen? So basically, psychologically, you have to be in the mood to break things, and that's not something that a programmer who built the project can always get into. And again, maybe it's not that we're ignoring things, maybe we're trying to still be good testers and all that, but under the hood, in your subconscious, you're probably not trying all the inputs and outputs that you would to break it, right? Let's run a brute force cracking algorithm to just run through as many inputs and outputs as possible, for instance. So that's the psychology of it. Economics is another thing, which you're probably not going to hear anywhere else other than in a software engineering type of class. Every class is going to tell you, yes, test your software, make unit tests, do all of your testing procedures. Absolutely makes sense. Do you know how much time it takes to do testing? Is that ever talked about? It might not be. So one of the types of testing that we can do is called exhaustive testing. And black box or white box doesn't matter. You're basically checking every single combination of values, every single path that the software can take. And black box versus white box, can't see the inputs, so you're just checking inputs and outputs. White box, we can see inside, so we're checking algorithms. The question becomes, is this feasible? Right? Is this something that we can actually do? And the answer is absolutely not. Exhaustive testing may make sense, but it's not possible in any way, shape, or form. So let's walk through a quick example here. Systematic testing is basically what we're getting towards. But here's the simplest example in the world, okay? So we have a sum program, return A plus B. Stupid simple program, right? One basic function. Well, if we were to exhaustively test it, and again, exhaustive means check every combination. That means we're doing a combinatorial check of the entire space of integers that can be combined here. So 2 to the 32 times 2 to the 32 equals about 10 to the power 19 tests that would be run just for this function. So that is 600 years of testing. Okay, we're making assumptions here. We're assuming these are running sequentially, right? So we parallelize it, we get a speed up. But what is the speed up factor for 600 years? It's not going to be still feasible, right? One test per nanosecond is probably about right. Let's check A plus B. We get an answer very quickly. Again, exhaustively testing becomes impossible. And, scale this up. This is a 32-bit system because we're assuming integers are 32 bits here. This would be 2 to the 64 times 2 to the 64 if we're on a, common current gen system. Even longer to test. So this is what exhaustive testing means. It's not feasible in any way, shape, or form. And again, this is one function from probably a bigger program, right? So not going to do exhaustive. You may hear about it. You're going to say it's impossible. We're not going to do it. We'll be smart about things. Everybody good so far? hopefully. I like testing, it's a lot of fun. I also like breaking things. Shouldn't be no surprise to the majority of you here, though. All right, so let's talk about the purpose of testing, assuming we're all good then. Let's get a party parrot up in here to liven things up. There we go. So why do we do testing? And what's its objective? Basically, we want to try and make sure that our programs are feasible to release, right? We want to get to that good enough magical state. The issue is that testing is often done at the very end. So we do all of our development, all of our mental work with requirements, with design documents, all that mental effort is front loaded. We do lots of development, and then at the end we test, right? And it's usually thrown together. Um, Time is short, budgets are exhausted, managers are nervous, customers are anxious. Testing is the last thing that we do. And that's when we find all the problems. That's why test-driven development is kind of a nice thing because we interleave it as we go. But this is not the right way to do things, right? If we have a good testing plan, we don't get into this test at the very end. Oh crap, we found a game-breaking issue or a major flaw in our software that causes us to redo all of our development. So if we follow good testing strategies throughout development, if we follow, proper testing procedures, we can avoid all of this headache and crunch as well. So the question becomes, okay, we know we have to test and we'll do it throughout, right? Let's do it when we make releases. Let's do it to integrate all throughout the software development. How do we find as many errors as possible in the least amount of time with the minimum allocation of resources, which is basically you, the tester, or the amount of time that you have to spend on project A, B, C, and F, or something like that. So how do we do the most work for the least amount of effort is basically the question. Well, we're going to have, surprise, surprise, a process. Now, this allows us to get things done quickly. We're going to look and we're going to test. And when I say testing, I'm meaning like verification and validation. We're going to use them kind of nebulously here. Let's check the configurations of all of our artifacts. So check our requirements, check our design docs, check our source code. Let's get everything into a configuration tool where we can very easily evaluate them. Let's do the same thing with our tests. So let's generate test cases, let's generate test suites, generate test plans. Let's figure out what procedures we're going to run to do testing. Are we doing one-off testing every release? Are you doing a full system test whenever you push it up to GitHub? Doing like a Travis CI Jenkins pipeline type of thing? What tools are we going to use? Are we going to use JUnit? Are we going to use Nose or PyTest? Are we going to use Travis to do automated unit testing? What do we want? With our test cases, we're going to specify what are the expected results. We're going to specify the inputs and outputs. So basically, we're going to get all of our ducks in a row. We're going to build out another software artifact, and we're going to call it our test specification. Effectively, we're going to have a good plan for how to do things. So let's figure out some principles here. The absolute necessary required part of a test case is the output, the expected output. So this is the oracle, it's also called. The software test oracle tells you if your test case passes or fails. And all that means is that we're expecting some output, does whatever we put into it, match what we say it should. Okay, we all know this at this point. Don't test your own programs. Other thing, the programming organization should not test its own programs as well. So if you're a development house, you should probably have another organization doing testing. And this could mean like contracting out to another group within your company, right? You don't always go find a contractor or something like that. But thoroughly check the results. So actually go through the test report, fix all the issues, and write test cases for valid conditions and invalid conditions. So again, if I'm writing a phone app and I'm expecting, okay, I'm expecting the user to use the little joypad that I'm drawing on screen. Well, what if the user starts like doing it in landscape mode instead of portrait? I never developed a landscape mode. So if the user is holding the phone like this, he sees a little like tiny scrunched up window because the screen auto formatted to landscape. And then maybe all of the information that the user needs to see is not drawn on screen or something like that. So basically follow good guidelines, follow good principles here. Other things to do. Um, okay, figuring out what the program is doing and if it's doing it correctly, absolutely necessary. Also check to see if your program's doing weird things that you don't expect it to do. Right? If it starts chattering on a network connection, it shouldn't be doing that. Why is it doing that? Colors are kind of off on a particular operating system. Why is that happening? Basically, make sure that you know exactly what's going on. Don't pad your test spec as well. Don't add on junk test cases because that just wastes everybody's time. Don't plan your testing to not find any errors because that's never going to happen. And let's see, testing is extremely creative and intellectually challenging. Um, don't just think testing is the let's get it done type of thing at the end of the project. It can be just as hard as programming the entire thing. So don't discount testing is kind of the key takeaway here. So let's talk different types of testing now. And that's probably going to take us through the end of class here. So we talked about V&V. We talked about guidelines and the mindset. Now we're going to talk about some of the different types of testing that we can do. I said we're going to need a strategy for testing. So start testing things individually, and as you go, broaden your scope. So here you see kind of a little flow chart of our testing granularity. So we start very, very, very small, very minute. So that's going to be your unit testing. We're happy with that. Move on to integration testing. Again, bring multiple modules together, see if they still work. Add on new tests for integration. Then we're going to do validation testing. So this could be making sure that our project meets what the customer is doing. Then you see system testing. Make sure everything's working as a whole. Now, if you look at this figure, you might see and might think that it's kind of different than what I said last time, right? We do module, then we do integration, then we do regression, then system, then acceptance. Again, your testing strategy may differ from company to company. But as long as you're hitting all the key beats, you should be relatively in the clear that your software is quote unquote good enough. All right, so unit testing we've kind of beaten to death with test-driven development, so I'm not going to spend a whole lot of time here. If you have any questions on this, again, feel free to drop it into the chat. But unit testing is where we have the smallest, most atomic bit of software that we can check. You're checking a function call, you're checking a class member, you're checking a module, something small, right? This is something that you can accomplish with a JUnit test. Typically, you do this early on. You can start designing your use cases when you do your requirements. So if you're doing test-driven development, we're writing test cases first and then code. Maybe we don't have everything we need at this point. So if we are referring to other classes, if we're referring to other modules, other functions, you're probably going to have a lot of stubs, right? So a stub is going to be an empty bit of functionality just to make your program compile. And you're going to have like a to-do fill me in later or something like that. The driver might be the thing that calls the function if it needs to be called. But unit testing, tiny little bit of software. Now here's actually a question for you, which this is kind of a good thought experiment, I think. Let's say that we have a class that we're testing. So this is a class under test. If you ever see the acronym CUT with respect to software development, that's class under test typically. So let's say that we have a test case, a test suite, list of test cases here. Checking this particular class, we have a dependency that becomes apparent. So we're linked up here. Our class under test is dependent on some other classes. are there any issues for our test cases in this point? So let's say we have a class. Let's bring in other classes. So this is, let's say, class main menu. This could be class option 1, class option 2, and we're trying to just test this thing. Is there an issue with our test cases now? Because this is where things get tricky with object-oriented programming. I guess any programming, really. No need to call out OO because this applies to everywhere. Any thoughts? Is anybody there? Or are we all working feverishly on our last week of class? If we don't say anything, he'll just keep going, right? Hey, thank you. If the dependency has an issue, hasn't been tested. Absolutely. So if we are bringing in other classes, do we have to test them as well? And that's kind of an ambiguous question, really. So we can actually kind of go into a little bit more example here. So this is the same thing, except now we've broken up the dependency. So class under test is dependent on this class and this class, where it turns out, oh crap, these are interfaces. So this is just a front-end class. We're abstracting out functionalities to other classes. So the actual code inside of dependency 1 is instantiated in concrete dependency 1, concrete dependency 1, concrete dependency 2 down here. Well, in this case, if we have the ability, right, this might be hidden from us behind like a facade or something. Maybe we have to add a test dependency in here. So let's maybe create function stubs for these dependencies, add them in, and then we're just going to reference these test stubs. It's possible maybe these don't exist, maybe they haven't been tested, maybe they're testing their own thing. But basically, once we start adding on relationships and adding on dependencies and all of those different ways we can link up classes, we have to make our test cases work with that. And maybe that means we stub them out. Maybe that means we bring them into the fold of our testing. So it just kind of depends what we need to do, honestly. But it makes things tricky, as you can kind of see here. All right, I use the term driver and stub. Now, the driver, this is going to be your quote unquote main program. So this is going to be what runs your test cases. It's going to take in test data. It's going to execute all your test scripts. It's going to return the results that you need. So if you're using JUnit, this is kind of baked in by right-clicking and hitting play on that test class, right? But if you're doing something in, say, C or maybe Python or something like that, you'd have to write your own test driver, unless you're using a external program. And then again, the stub, I mentioned this as well. This is going to be just an empty shell or a dummy program or something to just make sure things are instantiated in memory. Now, the issue is that these actually bring in overhead. So if I'm adding on drivers, I'm adding on stubs, I'm adding on, things that have to be instantiated in memory, things that have to be executed at runtime. Basically, I'm adding on to the overall complexity of my system. And one thing to kind of keep in mind when we do testing, there's this really interesting idea. If we are testing a program, are we changing its behavior by simply testing it? All right, so think of a program, and maybe the easy way to think of it is that it's testing itself while it's running. All right, so let's say we have a program that's executing, and we're running test cases in parallel. So we're actually doing runtime testing, which is a thing you can do. Right? So the program runs and runs, it executes a test every other cycle or something like that. By running testing, Okay, so based on this point here that you see, we're adding overhead. So we're increasing the amount of RAM that's being used, the amount of processor usage simply by testing. Are we actually impacting the execution of the program by testing it? This is a legitimate problem in software testing, by the way. Simply by adding this overhead, you can impact the results, and that's something that you have to kind of control for. All right, stubs and drivers we talked about. Let's move on to integration testing since we haven't really talked about integration or, any of these other ones in great detail here. So integration testing is another common one that you will probably experience, once you get into industry. This is where you bring together software modules, right? This is where things start getting stitched together into a whole package. You're probably just going to be responsible for one tiny piece of the puzzle, even if you're a senior developer, right? You're still working on a project, it's going to get integrated into something else. Integration testing has to be systematic. So you have to have a very specific process to follow for bringing modules together. And with that, we have to test to make sure that by bringing things together, we haven't brought new issues in, right? And again, things could be inconsistencies with data types, interface errors, basically lots of different things that can happen when software packages written by different people get thrown together. So we have some strategies to help out with this too. So we have non-incremental or big bang integration. So here is our big bang, here is our non-incremental view. We just do it all at once. So I've got 20 developers on my team. We're going to integrate all your modules at once just to save time. What's the problem with this? I can't even keep a straight face. If I'm bringing together 10 different modules at once, how in the world do I know where the problems are going to be? There is zero way to localize things, right? Typically, you get chaos. You get a whole big amount of errors. And people will tell you, or they may think that this is a nice way to do it because it's just quick. You do it all at once, no issues, right? That's assuming you don't run into any problems, which is never what happens in the real world. Typically, you want to do something more incremental. You want to bring in modules a piece at a time so that you can control for the results, right? If I'm bringing in module A and module B, let's take my two liquids here. Module A, module B, I integrate them, okay? Well, I can very clearly see there's a problem here. I'm out of coffee. It's awful. But I know exactly where the issue is, right? I can localize things, and that's a really weird example now that I talk about it. But if I start bringing in multiple pieces at the same time, you can get a lot of false positives. You can get a lot of weird moving parts that you just have no idea where the issue is, right? And it actually can take longer to fix if you do it this way. Whereas if you do it incrementally, piece by piece by piece, maybe the test cases take a little bit longer to run because you keep rerunning things. But then okay, the exact issue is in module C. We know that. Let's dig deeper to see what the issue is. Right, so to visualize integration testing, modules A through C, test them separately in unit testing, test them together in integration. However you put them together, again, it's going to be up to you. I would recommend incremental though, mainly because you can isolate issues, you can correct them in parallel, um, you don't have as many interface issues, and there's multiple ways we can do this too. So we could look at integration testing in an incremental perspective, either top down or bottom up or sandwich, which was the thing I skipped over here at the bottom. But you can basically visualize what this hopefully means. If we're doing bottom up integration, we're going to start with all of our separate submodules, and we're going to kind of bring them together, kind of separately. So let's bring together D1 and D2 into B. Let's bring module E up here. We'll call it C. Then we'll bring these two together. We'll test them. Then we'll bring them together into module A. So we're starting off with all the little separate sub-packages, kind of putting them together. Then we'll do another layer where we have two intermediate modules. Let's put them together. And then let's keep building up from the bottom. Right, top down would be the other side of things. Let's try to kind of look at things from a higher perspective. Maybe let's bring a bunch of modules together and then let's kind of tease it apart. So basically we just kind of have, oh, where I'm going the wrong way here, sorry. Just which perspective do you want to take with your integration testing? Start separate, bring together piecemeal, maybe start at the top and kind of go downwards down the chain. So maybe a more global perspective. Maybe you've composed modules together and now you're trying to kind of tease them apart as you go. Just depends on your perspective, I suppose. Sandwich, also known as hybrid, basically we're just kind of picking and choosing as we go. So it's kind of a mishmash of hybrid or bottom up. And I guess I should mention too that this integration, this does focus on testing, right? So we're running individual specific package tests more granular down here, whereas we might start with the more coarse grain tests at the top and then work our way down. Hybrid or sandwich testing, let's start in the middle and work kind of both ways. So let's start medium grain testing. So maybe we're checking our intermediate stages. Let's go up, let's go down. Just kind of depends on your strategy, right? So, integration testing. I would recommend incremental, but that's just from personal experience. All right, so how much more do we have to get through? We've got 4 minutes. Um, let's talk validation testing because I want to get through this. So we can skip this example. All right, validation testing. This was again where we make sure that our customer is happy with things. So we want to make sure that the customer requirements are being satisfied. And one way that you can get by with doing validation testing, if you're doing something like a web application, phone, or a game, let's do alpha and beta testing. You probably all have heard of this in terms of games or websites or something like that, where we have a very early alpha build. So that's your early access model if you're a Steam user. Let's release it. We are fully transparent. We know this is not done. What do you as the clients, the customers, the user base think so far? Are you happy? What do you like? What do you not like? Okay, fine. We'll take that into account. Let's do a beta build. Now we're going to do a closed or an open beta where it's a lot more feature rich. We're pretty much ready to go, but we're still fine tuning things based on what you, the end user, wants to see. Right? So this is where you can bring your customers into the fold here with your testing. All right, so alpha and beta testing then doesn't have to be game related, by the way. Could be actual application. If you're doing alpha testing, it's in-house, it's internal. However, typically you're going to bring people in, right? Let's bring in clients. Let's do user studies. Okay, which interface do you like better, A, B, or C? It's very controlled. Beta is typically going to be done at the end user site, at the customer site. Give them the software, let them play with it, collect feedback in some way, whether it's through surveys, whether it's through analytics, whatever you're doing. Basically, alpha is going to be in-house, beta is going to be kind of released, I suppose. So, last but not least, let's talk system testing, because this is something that we also haven't typically talked about in great detail here. 2 minutes, got plenty of time. Software is just one piece of the puzzle, right? So we have our software, we also have our requirements, we have our design documents, we have our hardware, we have our users. Basically, the system as a whole is going to be your entire package implemented somewhere and released. And now we're checking not only the inputs and outputs, but the impact of humans, the impact of the environment, of the hardware, of all this real world uncertainty, which can impact your program. And system testing will try to catch all of the issues that you might see in the wild. So what do we do? I will probably, let's see. Yeah, we're actually at the end. That's good. What kinds of system testing can we do? We can stress test, so we can give it heavy loads. We can give it large amounts of data. We can do usability testing, so let's bring humans in. We can do security checks to make sure that our software is secure and that we're not going to leak information. Basically, you can go through this laundry list of types of tests here, and you can kind of get across the fact that these are all high-level system as a whole tests, right? If I'm running a compatibility system test, I'm not doing a unit test here. I'm checking to make sure my mobile app works on Android, on iOS, on Windows Phone, um, on every phone that we want to support. Maybe we want to do procedures. So anything that involves people, we're going to do testing on to make sure they understand the procedure and that it's valid for them. So high level, try to catch everything at this point. All right, last slide here. I hit a bunch of slides in my presentation here because they're not relevant for you all, by the way. So there's a lot of slides on like testing and deliverables and all that. I made that extra credit for you so you don't have to worry about those. But if we're looking at what a test case is, we need a name, it needs an ID for traceability, we need a description, what type it is, what are its inputs, what is the expected output, and now since this is a real test case, what is the actual output? Does that mean it's a pass or a fail? What is it linked to? Okay, all done, right on time. Hooray. I will see you all Wednesday on Zoom. I will send out an announcement after class to that effect as well. Any questions, comments, or concerns? You've got office hours in 10 minutes on Blackboard. Otherwise, look forward to seeing all of your smiling faces on Wednesday. So, goodbye, everybody. Hope you have a wonderful rainy Monday, and I will see you next time. Bye. You as well. Thank you. Good luck with wrapping up your term projects.